All right. So we left off on Monday talking about how do eukaryotic cells regulate gene expression after the mature mRNA has left the nucleus, right? So you've already lost being able to regulate it at the level of transcription. You've even lost the ability to regulate it at the level of maturing the mRNA, although this first statement talks about the mRNA. And so how do you regulate it past there? Now, you brought up a question, I think, Josh, like, can't you just not put the poly-A tail on, right? And that's absolutely what you could do, or you could put a really short one on. Both the 5' untranslated region where the guanine cap is and the 3' untranslated region where the poly-A tail are, both of those have a large influence on how long the mRNA lasts in the cytoplasm. The shorter the poly-A tail, the shorter it's going to last. The less complex the 5' untranslated region, the more readily it's going to be deteriorated. Well, really, actually, the less it's going to be translated. It's not going to deteriorate it any more quickly, but it's going to make it to where it binds with fewer ribosomes in the amount of time that it actually lasts. But where it becomes really interesting is of actually, like, assuming you kicked it out and you built a really great long-lasting mRNA that was going to be translated into a lot of protein. And then the signal changed. And you realized that what you started, you're already well on your way to doing something you don't want to do, to doing something that's going to be very energetically costly. And then we talked about this last time. You just design an RNA with the complement of that mRNA. You send that out into the cytosol, and it's going to bind to that mRNA and prevent it from binding to ribosomes. And then basically neutralizing it until it gets deteriorated by nucleases. It's wonderful. It's wonderful. It's like you paid somebody to go and kill someone for you, and you've already done it, right? It's gone. But then you send somebody that will just go and hug them until that person finds out and everything is good, right? Which, I don't know why, but that sounds like a really funny thing in my head, of just sitting there hugging an assassin until everything can be neutralized. And I don't know why I thought about killing somebody. I don't know. I'm sorry. All right. One last question we need to deal with. So now you've already translated it, okay? So you didn't neutralize the mRNA, or maybe you did, but before you neutralized it, you've already made protein product. And not only was that energetically costly, but now that protein is forcing the cell to do something that you don't want that cell to do, right? So maybe you responded to a signal saying that the environment, I don't know, was heating up, and so the cell is now kicking out excess fluid to try to cool the external environment down, but the external environment dropped back down in temperature, and you don't want your cell kicking out extra fluid, right? But now you have all these aquaporins and things that are pumping, or ion channels that are pumping ions out, and water's following, and you need to stop that. And so now you can't just neutralize your mRNA and stop making protein. You've got to do something with those proteins. You've got to destroy them. So this is what you do. And by you, I mean virtually every cell in your body. You mark the protein for destruction. There are several ways you can do this. The most common tag is ubiquitin, which is a protein tag. And so you basically tag the protein with a ubiquitin tag. And then once it gets that tag, the machinery, it's going to recruit machinery that will come grab this protein and will put it inside of this core. And this core unfolds the protein and basically does what cooking something does. Mm-hmm. So like when you cook an egg and it takes all that albumin in the egg white and unfolds it and solidifies it, that's what happens with the protein when it gets put inside of this chamber. It unfolds it and then starts breaking down that protein. So you mark it for destruction. And once it's tagged, the machinery come and grab it and force it into that tube. So there's no escape. There's no escape once you get tagged. And so this is nice, not just for proteins that you don't want working anymore, but it's also nice for proteins that are past a certain age and are starting to lose efficacy, right? Are starting to just deteriorate and break down. And you put them into this chamber and you recycle those amino acids and make new proteins. And so it's actually a wonderful thing. Plus you can tag foreign proteins for destruction this way. I mean, you can basically tag anything for destruction this way. Yeah, Joey?
So like once those proteins are broken down into amino acids, are they essentially then coupled with like more anticodons to be made for more mRNA?
Yes. Yep. Yeah, then you would use those amino acids to recharge tRNAs using amino-acyl tRNA synthetase, the machines that charge those tRNAs, so that then they can be involved in translation again. Absolutely. Yeah, Josh.
Can't you just send it to like the lysosome and like you nature it that way?
You could. You absolutely could. The thing is, the lysosomes are oftentimes formed from vesicles. So vesicles that came in from the external environment is usually where lysosomes form, and then a vesicle full of digestive enzymes goes and fuses with that. So there's not a lot of machinery designed to take things inside of the cell to lysosomes. Lysosomes come from mostly external material that the cell's designed to eat and to break down. And so it's more helpful to have something that's specifically designed to deal with internal components. And then that way there's some higher level of control, because the only way to put it there is if it's tagged, right? It's got to be tagged for destruction, and it eliminates the possibility of taking proteins that are absolutely essential and having them end up in lysosomes. Yeah, that's a good thought. Any other questions, thoughts? We'll sum this up, and then we'll be done with chapter 16. Yeah, Joey.
Are there certain proteins that are like, or maybe but that are like self-regulating? So like, how some of
that they'll just unfold themselves.
Well, like they'll be turned on and off depending on the conditions within the cell.
Yes. Okay.
Yeah, and so some of those are activated by the particular chemical composition within the cell. So if the cell starts to have a lot of movement of ions, it can rapidly change the internal components of the cell. Typically, the inside of the cell is negatively charged. The cytosol of the cell is typically negatively charged, but during muscle cells and neurons, rapidly change the internal conditions of the cell to carry an electrical signal. And so when that changes, they can shift from being pretty negative to being really positive at the same time. And that absolutely is going to influence proteins. Yeah, absolutely. All right, so let's sum this up. So proteins can be chemically modified, which alters activity. So you could just slap a phosphate on it, which may be an off switch for that protein, or you can slap something else on it that's going to be an off switch or an on switch. You can process these proteins. So many proteins are actually made in an inactive form. And then so not only do you need to make the protein, but then you actually need to activate it by either removing a piece or phosphorylating it or doing something. So you could actually make a protein in response to a signal and never activate it. And then that protein just kind of hangs out until it gets destroyed. Or you can degrade them by proteasomes after they're marked with an ubiquitin tag. All right, so you can do all sorts of things with the proteins that you make. And so I don't know. We tend to have this idea. I mean, I guess it sort of makes sense, but we tend to deal with things in our own lives. Like if you've invested a lot in something, you've got to deal with it, even if it's not good, right? It's like, because I put a lot of investment into this, and a lot of really horrific business decisions are made based on that, right? We've already invested a lot, so we need to make this work. Living organisms don't behave that way. It doesn't matter how much a cell has invested in making a protein, it will willingly give that protein up and just, count its losses. Living organisms do this as well. You see birds all the time will lay eggs and then abandon their nest. And they've invested an enormous amount of energy into laying those eggs and producing the developing embryo, and then they'll abandon it if they don't have the resources to continue. And so living organisms, living cells, they don't behave that way, even though we tend to behave that way. Yeah?
Are lysosomes and proteasomes the same thing?
Well, proteasomes, some lysosomes would qualify as proteasomes if they're digesting proteins. And so what makes it a proteasome is it has specific enzymes inside for digesting proteins. If that makes sense. The proteasomes, though, here we're dealing with it tends to be chambers for proteins that were made by the cell versus for proteins that were made externally and eaten by the cell. All right? Any questions, thoughts, concerns? Things you feel like you want to share with the group? I'm sorry I didn't tell you some of these ideas of evaluations before you did your cafe, but I guess David has still yet to complete his.
I just did it.
Oh, he just did it, and Molly
And,
Molly just did
I
hers.
just want to say what I suggested is a trip to the Bahamas in the group class. I hope they come
trip
through with that.
to the Bahamas.